The title of the paper is Fracture Toughness of Matrix Cracked Fiber Reinforced Concrete and Functional Graded Concrete Beams Using Equivalent Two-Parameter Fracture Model. All fracture models calculated fracture parameters from a three-point bending test using through thickness cracked concrete beams. However, in fiber reinforced concrete beams, fibers must cross the two surfaces of the pre-existing crack to have actual field condition. Recently, Salam and co-workers suggested a methodology to create a pre-matrix crack in fiber reinforced concrete, which represent the actual field condition in which the fiber bridging the crack surface. To do this methodology, we will estimate the fracture toughness of matrix crack functional grade concrete and fall depths fiber reinforced concrete beams using the equivalent relationship of TPFM. Check the reliability of estimated fracture toughness using the maximum size of the non-damage defect concept. Three mixes, including normal concrete and fiber reinforced concrete and high strength concrete, were designed for the experimental program. Fiber reinforced concrete were designed by adding 1% hogged end steel fibers by volume fraction to normal strength concrete. Steel fiber were used with a length equal to 35 milli and circular cross section. 48 matrix cracked full depths fiber reinforced concrete and functional graded concrete beams were fabricated with constant breadth equal 150 milli. The initial crack to depth ratio stayed equal 1/3. The beams are divided into three groups according to the span to depth ratio L/D equal 4, 5, and 6. Functional grade concrete beams were divided into three equal layers. The bottom layer is made of fiber reinforced concrete, and the middle layer is made of normal strength concrete, and the bottom layer is made of high strength concrete. This figure shows the matrix crack approach and the process and of doing the matrix crack. This table shows the estimated fracture parameters K1C and the crack tip opening displacement by the equivalent two-parameter fracture model for different beam sizes. To do this, or to check these results, reliability of the predicted K1C from equivalent two-parameter fracture model for matrix crack, full depth fiber reinforced concrete was examined at first cracking and maximum stress by the concept of maximum size of the non-damage defect. And as shown in the figures, the results show that the Dmax over the nominal maximum aggregate size for the matrix crack full depth fiber reinforced concrete at the first cracking and the maximum stress ranged between 101 to 1.54 and 1.38 to 2.89 respectively. To sum up this work, in the case of matrix crack full depth fiber reinforced concrete beam, the first crack initiation appeared before the maximum stress. However, the first crack initiation occurred at the maximum stress for matrix crack functional graded concrete beams due to the absence of steel fiber ahead of the crack tip. The presence of the softening portion in functional graded concrete beam specimen reflects the efficiency of the proposed new matrix crack technique in simulating a real field crack in the laboratory. The predicted value of K1C for matrix crack specimen estimated by equivalent relationship of two-parameter fracture model are appropriate according to the maximum size of the non-damage defect concept.